Okay, in this classwork, we are going to go further into one-way ANOVA, or one-way analysis of variance. So as usual, there is the option to complete this as the PDF file, but I encourage you to follow along as we work through this. So this classwork uses this JASP file, pain data. So I'm going to go ahead and download that and open it up. So a pretty simple data set here. We see we have 30 cases and 2 variables here, pain and condition. So let's go ahead and find out more about this. As a note, you don't need to be able to run this analysis in JASP if you aren't able to access the software. You can also, if you aren't able to access the software, you can access the results that we get in the output in this Google document. Now, the purpose of this classwork is to further examine the use of ANOVA to test for differences among 3 or more groups. We'll practice conducting a one-way ANOVA using JASP and writing up those results in APA style. We'll also highlight in what ways t-tests and ANOVAs are similar and different. So our example we'll be running is regarding pain reduction. Now, a story by Patty Namond, reporting for NPR, describes a study investigating the role of music in pain reduction. The study used 3 groups of kids, all recovering from surgery. The kids either 1. Listened to music, 2. Listened to an audiobook, or 3. Sat with noise-canceling earphones for 30 minutes. The researchers found that kids in both the music and audiobook groups experienced pain reduction levels comparable to over-the-counter pain medication, while the control group enjoyed no such benefits. The research used the 10-point FACES scale, which can be a useful way to collect data from humans who don't have the best vocabularies or limited communication skill. And here's an example of what that looks like. We see the Wong-Baker FACES pain rating scale, where a 0 indicates no hurting, 2 hurts a little bit, 4 hurts a little more, 6 hurts even more, 8 hurts a whole lot, and 10 hurts the worst. So even young children are able to look at these faces and use the faces to indicate how much pain they're in at the time. The following variables can be found in our data set here. So we have pain, which is a measure of pain using that FACES pain rating scale. So on the scale of 0 to 10, how much pain they were in after their surgery. And the second variable is condition. So which condition they were randomly assigned to. 1 being audiobook, 2 being music, and 3 being the control group. So I'm going to go ahead and open this by clicking on condition, just so I can add these labels in here to make it easier. Two is music and 3 is control. So now I can see that I have these groups. And here, really, since this is on a scale from 0 to 10, since it's on a scale, it really should be in here as scale. So we have pain scale and which condition they were in. Now in this scenario, what is our null hypothesis? Well, the null hypothesis in ANOVA, similar to in t-tests, is always going to be that there is no difference. So in ANOVA, this really translates to being that there is no difference between any of our groups, that there's no difference anywhere. So how we would indicate this using our more formal notation, we could say, I'm going to make this a subscript and then turn it off. Oops. Okay, so our null hypothesis is that all three groups are the same, that there is no difference in our three groups. And so thinking about what ANOVA is testing, at the end of the day, what we're really going to be looking at is whether our three means, our means of each of our groups, are equal. So I'm going to indicate here, I'm using mu because we're talking about not just within the sample, right? We can look at the numbers for the sample and say whether one group, had higher pain than the others. But what we really want to know here in this research scenario is in the wider population, is listening to an audiobook or listening to music an effective pain management technique or strategy or treatment? So we start out by assuming that no, listening to an audiobook or listening to music will have no difference on their pain levels. It will be essentially the same as the control. All three we expect to be the same if there's no difference. So because we have three groups, we're going to end up having three means here. And we want to indicate that we are differentiating them somehow. So we can use the 1, 2, 3. We could also use maybe A, M, and C for audiobook, music, and control. Right? Whatever is going to help us indicate that really we're talking about three distinct potential populations. So here I'll go ahead and say that the mean of group 1, we expect under the null hypothesis, we assume that that mean is no different from the mean of the second group, which is no different from the mean of the third group. That the means of a population of people who listen to audiobooks and of people who listen to music and people who don't listen to anything, that there's no difference in their pain levels after surgery. So that is our null hypothesis. No difference between any groups, or essentially that all the means are the same. So when it comes to our alternative hypothesis, this is a little different potentially in ANOVA because we have different possibilities under the alternative hypothesis. If our null is that there is no difference, then our alternative is that there is some difference between any groups, really, that all the means are not the same. Now, under our alternative, it could be that, I'm going to need to get my symbol here for not equals. Not equals. So it could be that none of the groups are the same, that audiobooks are different from music, are different from control. That could be that could be an option under our alternative that makes it true that not all the means are the same, right? In this case, not all the means are the same. We could also have that maybe these two are the same, but these two are different. in this scenario, it's still true that not all the means are the same. It could also be that these two are different and these two are the same. Still true that they're not all the same. And finally, it could be that, wait, do we have another option here? That 1 and 3 are the same, but they're somehow different from 2. Right, that. Let's move this. That these two are the same, but they're different from this one. Right, so we have all these different possibilities that would all make it so that not all the means are the same. The opposite of all the means are the same is that not all the means are the same. Okay. So this concept that we have different options to our alternative, that if we know that they're not all the same, we don't necessarily know which one of these is true. This is why we will have to do a post-hoc test here. Okay? But we recognize that the alternative is simply that, right? The alternative is that not all the means are the same, that there's some difference somewhere in there. Now, in this scenario, what's our dependent variable? What is the thing that we think depends on something else? Do we think that which condition they're in depends on how much pain they're in? Or do we think that how much pain they're in depends on which condition they're in? So in this case, pain is going to be our dependent variable. We want to know whether pain levels depend on which condition they were in, and those conditions being audiobook, music, or control. Right, so we have 3 options, and we want to know, are there any differences among these 3 options, these 3 categories? Now, to run this in JASP, we're going to do a one-way ANOVA. And this is called a one-way ANOVA because we have one independent variable. So a one-way ANOVA has one independent variable, but our one independent variable has 3 levels. The fact that we have more than 2 levels means we cannot use a t-test. T-tests are only appropriate when we have 2 levels. So if we were only looking at music versus control, we could use a t-test here. The fact that we now have 3 categories we're examining means we can no longer use a t-test. There's nowhere to put a third mean into the formula for a t-test. It just does not work. So we have to use a different method when we have 3 or more levels to our independent variable. So in this case, the most appropriate, most straightforward test to use would be the one-way ANOVA. So we'll run our one-way ANOVA in JASP. So I'll demonstrate this here. Let's see if I can perhaps move a little bit bigger. Not much. Okay, so we are going to go to our ANOVA option, which allows us, you see when we hover, we can evaluate the difference between multiple means. Versus t-test, we evaluate the difference between 2 means. Okay. So since we know we have 3 conditions, 3 levels, we need to use ANOVA. And in this case, we're going to use the one-way ANOVA, which is listed as simply ANOVA at the top. We won't be getting into these more advanced forms of ANOVA in this class. Those are more advanced techniques. So once we open our ANOVA menu, we're going to select our dependent variable, which in this case is pain, and move it into our dependent variable box. And you'll note that it will only accept a scale variable here, which is why it's important that we change this to scale. If you're not able to move yours over, it may be that you haven't changed yours to a scale variable. Now we are going to move our independent variable to our fixed factors box. And we will select for a few additional options here. So scrolling down, I want to see my descriptive statistics. That will show me my means and standard deviations. I would also like to see the estimates of effect size. And generally, you'll see reported for ANOVA either eta squared, that's how you say this one, ETA, it's another Greek letter. Eta squared or partial eta squared are generally what you see reported. We'll just go ahead and leave the default here. And then if we go down to our descriptives plots option and expand that menu, we're going to move condition to our horizontal axis. So what this is going to do is it's going to plot our descriptives for us by putting the condition, those three levels, on our horizontal x-axis. So we'll see audiobook, music, and condition, and then we can see some descriptives, the means essentially for those three conditions. It's also helpful to look at our error bars, and for different purposes, you may want to look at either your 95% confidence interval or your standard error. Both tell you useful information. In this case, we'll go ahead and display the standard error. Okay, so here's what our menu looks like, and let's take a look at our results. Now, we're going to be writing up our results, again, in APA style. This is one of the most commonly used ways of communicating research and statistical findings in many fields, not only psychology. It's the American Psychological Association, APA, but not just in psychology and not just in America. It's also used pretty widely in the social sciences and education, lots of different fields. So learning APA style really gives you the ability to concisely and directly communicate research findings in a way that is understandable to others who have that training and background in research and statistical analysis. So it gives us a common language to use, a common way of presenting things so that we know, oh, this number in this space always means the same thing. So in writing up our APA style, the basic format for a one-way ANOVA will include a few things. So it's always good to start out, if you are offering it as kind of a standalone report, right, not as a larger piece, you want to give a sentence that tells the reader what is being tested. So really orienting your reader to what your purpose is in conducting the analysis. Why are you conducting this analysis? And then, so we can see an example of this here. This analysis attempted to examine whether students of Dr. Graham's statistics course outperformed students of Dr. X and Dr. Y on a test of quantitative reasoning. And this is a completely made up example. But you'll note that that first sentence is really, again, telling the reader, this is why we did what we did, or this is what we did. Then you'll follow that up with a sentence that says whether your result was significant or not significant. And we'll be looking to our p-value to help us identify that. So whether your result is significant or not significant with the relevant values from the output. So this is very important because your sentence, what you are stating, is your claim. You are claiming that there is a significant difference among the three classes, according to this example. So we include what test was run, a one-way ANOVA, and then what did we find? Indicated that there was a significant difference or a non-significant difference, right? Not a significant difference. So you'll indicate, depending on your p-value, among the levels of your IV. So in this case, 3 classes. That is the claim that you are making. What follows is then your statistical evidence to support your claim. So here we include F in italics, followed immediately by opening your parentheses, because what we're saying here is using the F that corresponds to 2 and 19 degrees of freedom. So this is the curve of F that we're going to be using, because remember, F is a family of distributions. So this really sets which one are we looking at. And this is really, right, this 2 and 19 is based on our degrees of freedom between groups and the residual or within groups. Right? So those two values, which we will find in our ANOVA table under DF, are what get put into this place, which indicates which curve we're looking at. Then the number that follows the equal sign, again, always with spaces on either side. This represents that calculated F value. So the F that was calculated from our samples. And to refresh, if we go back to our guided notes on the F statistic, remember that conceptually, when we're calculating this F value, we're comparing the between groups variation, so that variation we see across our different groups, over the variation we see within our groups. So we're really wanting to look across. Do we see a much wider amount of variation indicating that these groups are different in compared to how much we see within them? So this ratio then gives us a way of determining whether these separate groups are really in alignment on top of each other, or are they spread out? Are they different? So this F represents a ratio of our between group variation over our within group variation. And when it's high, much higher than 1, that's when we start to see, well, depending on what these are, that's when we see that it's significant, as it is in this case. Right? So P less than 0.01, 0.001 means that this resulting p-value is smaller than 3 decimal places could indicate, right? So this is saying that the p-value that we get from this test is something below 0.001. It's so small that it's almost 0, is how I like to think of it. So what this indicates is that the probability of getting this result, if that null hypothesis is true, is less than a 0.1% chance, which is so low that we would reject that null hypothesis and say, okay, those classes are different in some way, right? There is some difference between these 3 groups, these 3 classes. So let's look at our result and practice writing it up in that APA style. So for the first part, we'll really only need this top table, ANOVA. And you'll note that I've highlighted the different pieces that we need in the table for our APA style write-up. And really, best practice suggests that we really should include this as well. But I'm not requiring it as part of your write-up in this class, which is why I haven't necessarily included it here. Okay? But it is best practice to include it. So keep in mind, we will be putting each of these statistical letters in italics to represent that they are statistical concepts, that they represent a statistical concept or value, right? F, T, P, M for mean, SD for standard deviation. I want to point out one thing here. So going back to our guided notes, looking at this, we see our between groups variation over our within groups variation is what gives us our F value. So just want to kind of highlight something that we see in all of these values because we don't need all these numbers ultimately in our write-up. We don't present the sum of squares or the mean square, but they're used as part of the calculation of F, right? We are dividing them to get to our value of F. So just to show you here, right? So SS over DF, that gives us mean squared, right? So if we come over here and we look at our SS, sum of squares, 29.6, divide it by the degrees of freedom, right? Like we see here, divide by 2, and we get the mean square, 14.8. We can do the same thing on the bottom, right? This condition, this is between groups, between conditions. On the bottom, this is within groups, that error or residual term. So how much variation do we see within our groups? Just that general residual error that is naturally expected within our groups. If we look at the sum of squares, 79.6, and we divide by our degrees of freedom of 27, that gives us our mean square of 2.948. So dividing across gives us the mean square. And then our overall F ratio is mean square between over mean square error within. Okay, so we're going to take our 14.8 and divide by the 2.948, and we get our F value of 5.02. So again, we don't need all of these. They're used in the calculation of F. And again, that F is based on these degrees of freedom. Okay, so just to kind of connect some of those pieces there. So here we've got our APA style write-up, and here this is just a space for you to practice, right? So we have this analysis attempted to examine what? And you can feel free to use your own words here, but it should make sense as a standalone sentence, right? So this analysis attempted to examine whether listening to audiobooks or music, you could say reduces pain, results in less pain, um, affects pain levels, right? That's generally what we're looking at in children after surgery. A one-way ANOVA, so you know what I used to look at my data, indicated there was and maybe here it would be good to list that third group, right? Whether listening to audiobooks or music affects pain levels compared to nothing, right? Compared to listening to nothing, to a compare to not listening. Right, so this is where it starts to get, this is where people struggle a little bit, and I totally get it. We just want it to make sense. So right here, I think what is missing here that would be more helpful is here it says between conditions, but we're kind of missing that there's a third condition. So maybe to examine whether, let's just say it more straightforward, whether pain levels are different between after surgery among children who listen to audiobooks, music, or nothing. There we go. I think that's more clear even than this example. And this is a skill that, again, you practice. So a one-way ANOVA indicated there was a, now here's where we need to say, is it significant or not significant difference? And here we want to look to our p-value. If our p-value is less than our alpha of 0.05, then we conclude that this probability is lower than 5%. The probability of seeing a result like this is less than 5% if the null is true. Since it's below the 5% level, we will then reject the null hypothesis, conclude there is a significant difference in pain levels between conditions. And our evidence for that is in italics, F, and then take it off, open parentheses. I'm going to indicate my degrees of freedom from this top table in my output, the degrees of freedom. Start with the one on top and then go to the one on bottom. So 2, 27. Close your parentheses, space equals space. And you always put a space after your comma as well. Now we're going to report that F value, the 5.02. Comma, space, and now my p-value. Remember to put your p in italics, equals 0.014. And I'm going to go ahead and add in, I hope it will let me copy it. If it doesn't, you can add it using the equation option. Does not need to be bold. Equals 0.271. So this is the write-up of the first part of this analysis. Now, I say the first part because since we have a significant result and we have more than 2 conditions, this means we will have to follow up with a post-hoc test. Right? So as mentioned in the previous classwork, when results of an ANOVA are significant, this tells us that there's a significant difference between at least 2 of our groups we're comparing, but it doesn't tell us which groups are different from each other. So in order to identify which groups are significantly different, we have to run an additional test called a post-hoc test. In post-hoc testing, we compare each group against every other group to see, okay, this pair, are they different? Now, this pair, are they different? This pair, are they different? And we compare them what we call pairwise. To do this, we use specifically designed tests that keep us from increasing our chances of making a mistake when we're drawing our conclusions. So we recognize that in hypothesis testing, our alpha level really represents, to some degree, it's our level of accepted error that we're willing to take, right? We're willing to be wrong 5% of the time in saying that, oh, I see an effect when there isn't really an effect, right? So we want to avoid increasing the chance of doing that, of saying, hey, I found something when there's not really something there. When we do multiple tests, when we're testing more than one thing, because each time we test, we are saying, okay, we're willing to accept 5% error on this. And if we're willing to accept lots and lots of error, then that error starts to add up, right? So if we're doing multiple tests in one, we need to adjust for that so that we're not inflating our chances of making a false conclusion. So the test that I recommend using in this class for that because it's pretty straightforward across the board. You don't have to remember a lot of, oh, if you have this many levels, do this, or if you want to be more strict or more lenient, do this. I say Bonferroni's correction is pretty standard. Go with that one. You'll be safe. So I'll encourage you to pause the video at this point, and based on the results above, should we run a post-hoc test? I already answered this for you, but document why we should in this case. Now, again, since our ANOVA was significant and we have more than 2 groups, we do need to run that post-hoc test. So to do this, we are going to return to our ANOVA menu, and I'm simply going to open back up the one I was working in. I'm just going to add it on to what I already did. So if you scroll down, you'll notice we have an option for post-hoc tests. And I'm going to expand that menu, move condition to the box on the right, and then over here on the right-hand side, I'm going to go ahead and take off Tukey and turn on Bonferroni. I'm going to leave it as a standard type on the left, and then down underneath, I'm going to select for flag significant comparisons, because that is going to put a little asterisk or a little star next to the pairs that are significantly different from each other. Okay, so coming back to my output, this is really the trickiest part of the output, or the trickiest part of the write-up and the trickiest part to interpret, I would say. So looking at what we had before, we had our descriptives. We see for audiobook, there were 10 children in that condition, and the average pain rating for those 10 children was 5, with approximately 1.8 points of variation on average. For control group, we see also 10. The mean rating was 7, and that varied by about 2 on average. And for music, those 10 children rated their pain levels at 4.8 on average, with their ratings varying around that mean by about 1.2 on average. So looking at these, we can see visually there are some differences, but we cannot conclude from this whether these are significant differences until we've looked at the tests comparing each of these directly. So the tests that we've run will allow us to say, okay, audiobook versus music, is this difference significant? Now, audiobook versus control, is that difference significant? And music versus control, is this difference significant? So the number of comparisons we do depends on the number of conditions we have, or the number of levels we have. In this case, we have 3. So ultimately, we're going to be making 3 comparisons. So audiobook versus music in our post-hoc test. So in our output down here, audiobook versus music, we can see there's a mean difference of 0.2 between those groups, right? The difference between the 5 for audiobook and the 4.8 for music is 0.2. We're going to come across, and we're going to come all the way across to that P-Bonf, P-Bonferroni. You know, it's corrected for Bonferroni, or using Bonferroni's correction. So according to this, there is no significant difference, right? This is not below 0.05. There's no little star. So there is no significant difference between audiobooks and music. What about audiobooks versus control? That's what we see presented in the gray row. The mean difference between the audiobook and control groups is 2. Right? We see audiobook was 5 minus control 7 gives us that -2. meaning that audiobook was too lower than control. We come across to the right and we look at our p-value, corrected p-value, and we see this is significant, even after we have adjusted for the fact that we're comparing a family of 3. So we would report that there is a significant difference between audiobooks and control conditions. And the p-value that indicates that is the 0.044. Now our last comparison is between music and control. Comparing music with control, we see a mean difference of negative 2.2, indicating that music on average was rated 2.2 points lower in pain than control. And this is also a significant difference since this p-value is less than 0.05. There's less than a 5% chance we would see this big of a difference between pain ratings of children who listen to music and pain ratings of children who don't listen to anything if music was having no effect. Like if it was truly having no effect, the chances of seeing this big of a difference is about 2.5%. It's below our 5% value that we've set. So the results of our post hoc testing get reported immediately after that first part of the ANOVA. So here is our full ANOVA write-up from our previous example, including the first part plus the post hoc, right? An example of a post hoc write-up. So you'll notice you have your sentence that indicates the analysis is examining this. A one-way ANOVA indicated there's a significant difference among our levels, and here's my statistical evidence for that. And because there's a significant difference with more than 2 groups, we conducted a post hoc test and Bonferroni corrected pairwise comparisons, revealed that one group, and here is the mean and standard deviation, those come from our descriptives table here. That's why we select for this, means and standard deviations. So Bonferroni corrected pairwise comparisons, our post hoc test, revealed that one group with their mean and standard deviation scored significantly better than a second group with the mean and standard deviation for the second group and the p-value that corresponds to this comparison. So group 1 versus group 2, the 2 groups that are listed. Then there's an additional sentence in this case. Dr. Graham's students also scored significantly better. So this means that group 1 is also significantly higher than group 3. So in this scenario, group 1 is significantly higher than group 2 and group 3. So we see all 3 sets of means and standard deviations represented. This particular p-value corresponds to the comparison of group 1 versus group 3, right? Because we have multiple p-values that we get in our post hoc result table. So at the end here, we see, similarly to this one where we have 2 significant results and 1 non, anytime you have other non-significant comparisons, this is particularly useful if you have more than one. You might say all other pairwise comparisons were not significant, and generally you don't need to give the exact p-values for all of those. You simply say that the p-values, p's, are higher than our 0.05 cutoff. Right? It's a way of summarizing that all the rest were not significant, meaning the p-values were higher than 0.05. We don't really care what they are if they're higher than 0.05. So our post hoc test write-up specifies what post hoc test was conducted. And in this class, I recommend really always using Bonferroni corrected. So you'll just use this phrase. You may see in other cases like a post hoc test using Bonferroni's correction, or if it's a different test, use post hoc tests using Sheffy's test or Tukey's test of significance, you'll see it listed what test specifically was used as the post-hoc test. So in this case, this would be your standard language that's easy to use. The mean and standard deviation of each of your groups should be included, and you include that directly after you mention the group for the first time. If you mention them more than once, do not repeat that information, right? We don't have the mean and standard deviation for this group again because it's already presented once. We don't need to see it again. Indicate whether each group differed significantly from each other group. So here, Dr. Graham, higher than Dr. X, Dr. Graham, higher than Dr. Y. The others, not significant. So X versus Y, not significant. And indicate the p-value from your post-hoc test table that tells you whether that direct comparison, that direct pairwise comparison, is significant or not. And keep in mind, again, each of these p-values in your post-hoc is telling you specifically, this pair, is it different? This pair, is it different? This pair, is it different? It's looking each pair one at a time, are they different? If our overall ANOVA is not significant, we don't even need this because that would mean that there is no difference. And if we look at this, we're just going to see more no differences. So we don't even bother if the whole thing is not significant. Now, again, this is the trickiest part of the write-up. And I think that it really helps to write out all of the groups and comparisons on a scratch piece of paper first to figure out which ones go together. So that helps you to craft your way of saying it in the most straightforward way. And this is true for me. You may end up having to write a few different drafts to get it right, and that's okay because revision is just part of the process. It's just like, if you say something it doesn't come out right, you just say it another way. So same thing here, practice. The more you practice, the easier it will get. Your ability with APA, your skill with APA will also increase as you go on and read more academic texts that are presented using APA styles. So as you see it and encounter it more, you'll start to develop more of that fluency as well. So as I describe here, in order to test for those significant differences, we're going to look down at our post-hoc test table. We'll use that p-value to indicate, to look for those ones that are significant versus not significant. And here is where I've kind of listed out what we described about, what does this tell us in terms of our different groups. So audiobook versus music, that was not significant. Audiobook versus control was significant. And music versus control was significant. So what I like to do is I look at the ones that are significant and I see, do they have anything in common? Because if they have something in common, then it makes it, I can sort of condense them into one sentence or one easy way of saying it. So if I look at, I see control here, and the control had significantly higher pain than the audiobooks, and control had significantly higher pain than music. So since control had significantly higher levels of pain than both of those, audiobooks and music, then that's going to be my most straightforward way of saying that. I will therefore write that Bonferroni corrected pairwise comparisons revealed that, or indicated that, or showed that children in the control condition or control group reported significantly higher levels of pain than children who listened to audiobooks or music. That's going to be my sentence, if I can remember what I just said. And then I'm going to put in my evidence afterwards. My numbers go afterwards so that I know my sentence by itself makes sense. Okay. So let's see if I can I know it's written there, but I'm going to try to just do it again from my brain. So Bonferroni corrected. That always makes me think rice-a-roni every time. Pairwise comparisons revealed that children in the control group reported significantly higher pain levels than children who listened to music or audio books after surgery. And then let me clean up my mess. Okay. So there's my sentence, right? And then I also can say, I also know at the end that the audiobook and music conditions did not differ significantly. And I'm just going to put in my P above 0.05, period. So here I need to go in and I need to report my control group. And put that so I know that's going to go there. I know I'm going to need to report my music. And I'm going to have to report my audiobooks. And for each of these, I'm going to have mean and standard deviation. And then for this one and this one, I'm going to have a p-value because that p-value is going to be comparing this with control and this with control. So music with control and audiobooks with control. We don't have a p-value in this first one because we're not comparing anything yet. We've just covered one group so far. So we need two groups to compare to get a p-value. So coming back to my output, let me find my means and standard deviations to put in, and then I'll add in my two p-values I need. So in italics, I'm going to do mean equals, and this is my control group. So my control group is the second line down, so 7.00, comma, SD equals 2.00. I'm going to round to 2 decimal places here. Significantly higher pain levels in children who listen to music. Next up is music with a mean of 4.80 and a standard deviation of 1.23 rounding. Here I'm going to, so I don't forget, I'm going to do comma, and then I'm going to say P equals because I'm going to put my P value right there. So I know that that one compared to the previous one, so the control group, is significantly different. Now I'll go ahead and let me put in my mean and standard deviation for audiobooks first before I go look at those p-values. So the mean for audiobooks was 5.00, standard deviation equal to 1.83 rounded. Don't forget, comma, and then my p-value is going to go in there. Let me scroll back down, find my p-values for my Bonferroni, and so which one do I need first? First, I need music versus control. So music versus control is the one that's on the very bottom of my table here. No, come back. Right, music versus control. Make sure you're looking at the right one that matches what you're saying. Music versus control, my p-value is 0.024. So I'm going to put in 0.024 right there. So now I know my music group compared to my control group, music was significantly lower. Control was significantly higher. And that's my p-value. And those are my means, so I can see that difference. Now, audiobooks versus control group. The p-value that goes in there is going to be the other significant one from our output. Audiobook versus control, 0.044. And that's it. So Bonferroni corrected, and you'll see two slightly different versions. One, one a little bit different, and one we see audiobooks first, but generally they cover the same information. So Bonferroni corrected pairwise comparisons revealed that children in the control group with a mean of 7 and standard deviation of 2 reported significantly higher pain levels than children. This is why it's always good to read your work. Make sure it makes sense. Than children who listen to music with a mean of 4.8 and standard deviation of 1.23, and that p-value is 0.024, or audiobooks, mean of 5, standard deviation of 1.83, and a p of 0.044 after surgery. So this sentence, if you were to ignore all this statistical number jargon in there, it would read as just a regular old sentence. And the audiobook and music conditions did not differ significantly. So we conclude that listening to either audiobooks or music can help with pain reduction, but listening to nothing doesn't help. Good to know, right? And that is, of course, what that, while these data are not the actual data that this study was based on, they are simulated data, but they reflect what this study actually found. So the citation is here if you would like to look it up. Or sorry, the link to the NPR study is there. So you can go ahead and look it up there. Okay, so what are the similarities that we notice between ANOVAs and t-tests? There are several. So both have, and I encourage you, before you look at what I write, I encourage you, think about it, list out what you can come up with, and then compare with what I've got here and fill in. Okay, so what are similarities you notice between ANOVAs and t-tests? If we think about what they do, they both look for differences, in means between groups. So, in addition to this, they both have categorical independent variables, aka groups, and quantitative dependent variable. Because we're talking about means, and when we're talking means, we're talking about quantitative. Here's another obvious one you may not think of. They are both hypothesis tests, aka inferential statistical tests, right? Inferential statistics. We use the same alpha in this class for both of them, 0.05, to indicate our significance level. And given that they're both looking for differences in means between groups, both have a null hypothesis that there's no difference between groups. An alternative is there is a difference between groups. Another one, they both use sampling distributions to underlie that statistical test that we do. So that's a lot, right? Some more obvious than others, and I'm sure we could probably come up with some more if we really tried. Now, what are the differences between ANOVA and t-test? And again, I encourage you to pause and reflect and note as many as you can think of before you check out the rest. I was hoping this would work better. Let me see. There you go. Now I can type my answers in here. Okay. Well, here is an obvious one to start with. T-tests use the T-statistic. I guess I don't really even need that. And I wonder if I can. I want it at the top too. Okay, well, and this one uses the F. Oh, there we go. Statistic. Statistic. Okay, let's make this bigger. Now our T is a two-tailed test because of the shape that we have. So if you think of that one, we've got this curve that has the tails on both sides that represent our rejection regions. Whereas with our F statistic, as we pointed out, that one uses a one-tailed curve, right? One-sided, one-tailed because of this shape that we have and the fact that we're looking at ratios. So it's one-tailed because of shape. Now with a t-test, we only need 1 degree of freedom to determine which curve we're looking at. Whereas with F, we need 2 degrees of freedom. So when you're reporting, we have T degrees of freedom, right? Just 1 versus, for consistency, let me put that there. Versus with F, we have degrees of the first one and the second one. Okay. With T, we can compare only 2 groups or 2 means. With ANOVA, we have the ability to compare 2 or more groups. And with t-test, since we are only comparing 2 groups, so if we get a significant difference, we know that the difference is between those 2 groups. Since it's our only option, we have no need for post-hoc testing. Whereas with ANOVA, because we have different possibilities of what the alternative hypothesis might look like if the null hypothesis is not true, we need post-hoc testing if, again, we have more than 2 groups and a significant result. Okay, now for this last part, this is referring back to a piece we did in the previous classwork. So this last piece is going to be an option for you to practice writing APA style. So this is from the previous classwork. You can practice running it in JASP. I've included the data there if you like. But really, so why would we need a post-hoc test here? Really, the purpose here is to practice writing your APA style, paying close attention to italics and punctuation, where the different values go. And I linked the output from that previous classwork here. There we go. So that you can easily see it and the pieces that you need. right? So for writing up your one-way result, you'll need your F, degrees of freedom, your P, recommend eta squared. Since this is significant, you're going to practice your post-hoc write-up. That will include your 3 levels with their means and standard deviations, indicating which of those groups differ significantly from which other ones and which ones do not differ. Okay, so go ahead and practice putting that into a concise APA style write-up. And I encourage you, if you feel brave enough to post that to the discussion boards that you can then get feedback from your peers. All these answers are included in the solution for you to refer back to, and don't forget to post to the discussion board.